Okay, we have a suitcase sitting on a ramp and we're asked to find the acceleration of this suitcase if it slides down the ramp and it's subjected to a frictional force. Well, if it were just dropped off the edge of the ramp, the thing would fall down till it hit the ground, and it would fall with an acceleration due to gravity of 9.8 meters per second squared. That'd be the magnitude. But it's not going to fall straight down, it's going to slide down the ramp, and we're asked to figure out what that acceleration would be if it doesn't go straight down but goes down at that angle. We're given a couple pieces of information here. We're given its mass, so 5 kilograms, and we're also given that there's a frictional force that the suitcase is subjected to by the surface of the ramp, and that frictional force is 15 newtons. So let's set up to draw a free body diagram. I have another kind of just duplication of that angle there, and so here we go. We're going to, as always, represent the object with a dot, and we'll ask ourselves the 5 questions that we always ask, beginning with, is there gravity? Yes, there is. Gravity always pulls straight down toward the center of the earth, FG. And then the next question, is there a normal force? Is it sitting on a surface? And the answer is yes, it's sitting on a surface. We just discussed this ramp here. But the thing that makes this problem a little bit different from those we've done recently is that the normal force is, since it's always perpendicular to the surface, I have to twist or rotate my diagram to get this arrow being perpendicular to this arrow. So I'll draw in F sub n for normal force, and then while my diagram is still rotated, I'll ask myself, is there a frictional force? And the answer is yes, there is, and it's pointing in opposite direction that the suitcase would go. I guess I unrotated it there. The suitcase would go down the ramp this way, which means that the frictional force is pointing back up the ramp. So let me twist it again and just get that little arrow drawn in there. Okay, now what I want to do is establish my frame of reference by drawing some axes, and I think the blue and the red arrow probably suggest the reference frame that we're going to use, but let me draw it in to be very explicit. In the up direction, I'll call that positive y. Normally we do to the right being positive x, but you can see in this situation, if the suitcase goes, it's going to go down the ramp. It's going to go that way. So that means I need to change this up a bit and do to the left being positive x, which is not at all what we're used to seeing, but that's what this problem calls for. Now this is arbitrary, so it's okay that we have it kind of what we might think of as backwards. And then last of all, let's indicate here that this object is going to accelerate in the direction parallel to the surface, and that is the x-axis. So we've labeled the direction of acceleration, which is the direction of the net force down the ramp. Okay, and I forgot to draw in this label, F sub friction. Okay, so now that we've got those arrows identified, let's go ahead and add the rest of the information that we need here. First of all, let's acknowledge that this is 30 degrees here. And then what we need to do is we need to break the gravitational force F due to G. We need to break that into components because it's the only one that's not operating perpendicular to something. So what we do then, again, tilting the diagram, rotating it by 30 degrees, bring this arrow down here and bring this arrow over here like this, and those represent the y and the x components of force of gravity. So we'll say that this arrow in this direction is Fg, and here I tell what direction in the y direction, so that's the y component, and then this arrow represents Fg. Let me switch to a different color. This is Fg in the x direction. Now the length of this arrow here should be, on a free body diagram, a little bit longer than the length of this arrow, just because since they're opposite in direction, they can't be equal in magnitude if this thing is going to accelerate. So let me take this component right here and come over and just add it here, because this represents the component of gravity that is pulling this object down the hill. So I should have this green arrow being just a titch longer than this red arrow, and then the normal force arrow and FGY are equal in magnitude and opposite in direction. So if I wanted to go mark in that this is congruent to that and this is congruent to that, I could. Okay, so that lets me know what components are equal to one another. All right, so now let's go ahead, and we've got these arrows drawn in on our free body diagram, and the last thing to do in this video is to go ahead and actually write the expression for FGY. You know what? I think I'm just going to leave it rotated like that. It's easier to look at. So I'll say that FGY is equal to FG times the cosine of that angle. And the question, what is that angle? Well, this angle is 30 degrees, and hopefully based on your geometry skills you can tell that this angle here is also 30 degrees. So let me mark that as 30 degrees. Whatever the incline of the ramp, that's also equal to this angle right here. So FG cosine 30 degrees, and this in the x direction is equal to, let me rewrite it, FG in the x direction is equal to FG times sine of 30 degrees. And in our next video we'll have a look at how to write the equations based on this free body diagram that we have now finished. And for one last look at it tilted, I'll put it that way, and there we are.